So, good morning. Today, we will explore steady state control volume analysis, a cornerstone of thermodynamics for systems with mass and energy flow. Why is this important? Engineers use steady state analysis to design systems like power plants, refrigeration units, and jet engines. For example, in a gas turbine, fuel and air flow continuously and under steady operation, the mass and energy entering must equal to the mass and energy which is leaving to the systems. This balance ensures predictable performance. Now we will see the next important topic, that is the introduction to steady state control volume. A control volume is defined as a region in space like a turbine, compressor, or heat exchanger, where we analyze energy and mass interactions. In steady state conditions, properties such as temperature, pressure, and velocity at any point within the control volume do not change over the time. This simplifies analysis because we ignore transient effects. Let's consider a practical example. Sorry for disturbance. Now let's consider a practical example. A steam turbine in a power plant. Steam flows in, does work on the turbine blades, and it exits. Under steady state conditions, the mass flow rate of the steam entering equals the mass flow which is leaving from the steam turbine, and the energy transfer in form of heat and work also remains constant. Without steady state assumptions, modeling such system would be very much complex. Therefore, in this study, we are going to break down the principles of mass and energy conservation, solve certain numerical problems, and explore real-world applications. So let's start. Now we will see what are the steady state conditions. A steady state condition means no accumulation of mass or energy within the control volume over the time. Imagine a pipe from which water flows. If the inflow of water and outflow do not match, the water level in the pipe may stay constant. That is, if it cannot be in a steady state. And if the inflow and the outflow match, the water in the pipe stays constant. And this is called as a steady state. So what are the key important points for the steady state? The first is constant mass flow rate. The mass which is entering to the system must be leaving outside the system. Second is constant energy flow rate. The energy such as heat and work which is entering the system must be equal to the energy output coming out from the system. Now third is the time invariant properties. So what are the time invariant properties? They are temperature, pressure, and velocity. Therefore, the temperature, pressure, and velocity, which are time invariant properties, at any point should not change with respect to time. Now, take an example of a compressor. What is the purpose of compressor? The compressor is used to compress the air. Now, if the compressor is used in a jet engines to operate under the steady state conditions, we see air is entering at 5 kg per second, and this air is getting compressed, and it also exits at the same rate. If another airflow of 2 kilojoules per second joins the system, the exit flow becomes 7 kg per second by ensuring the mass conservation. So what does this mean? Steady state assumptions lets engineer design without worrying about the fluctuating conditions. They can focus on optimizing parameters like pressure ratios or the turbine efficiency. However, a real-world deviation such as startup, shutdown phases requires the transient analysis and which is more complex. Now, let's now formalize these ideas with certain equations that we are going to see in the next slide. Now, we are going to see mass conservation in a steady state. The conservation of mass principle states that mass cannot be created or destroyed. For steady state control volume, this simplifies to summation of all the quantities of mass which is coming inside the system must be equal to summation of all the mass which is coming outside the systems. Now here there is one term which is called as a mass flow rate. The mass flow rate is defined as density of the fluid multiplied by velocity of the fluid multiplied by the cross-sectional area. Now, let's apply this for the case of the compressor. Now, the air inlet is 5 kg per second. Additional air which enters is 2 kg per second. So, the total mass which is exiting from the system is 7 kg per second. Now, this equation is very much foundational. For instance, in a nozzle, if the air enters at 10 kg per second, it must exist at 10 kg per second, even if the velocity increases or the pressure drops. Okay. Now we are going to deal with the energy forms in the control volume. So the control volume, the energy exists in the 4 forms. That is the internal energy, which is due to molecular motion or the molecular motion energy. If the steam is at a high temperature, we say it is having more internal energy. Next is the kinetic energy. It is energy from the fluid motion. For example, if air is speeding through a nozzle, so it gains a kinetic energy. Third is the potential energy. This energy is due to elevation. For example, a water which is stored in a dam at a particular height possesses potential energy. Next is the flow energy. The flow energy is the energy needed to push fluid into or out of this control volume. Now take an example of an hydroelectric power plant or hydroelectric dam. Now here the water is stored at a particular height, has the potential energy. Now when this water from the height falls at the down, we say its potential energy gets converted into kinetic energy, and this is used for spinning the turbine. And the flow work is done to push the water through the pipe. Now mathematically, this energy, total energy of the system per unit is given by energy E is equal to internal energy plus kinetic energy plus potential energy plus flow work. The flow work is a multiplication of pressure and the specific volume. Now, in case of the steady state conditions, when the energy is entering via mass or heat or work must be equal to energy which is exiting. This leads us to the first law of thermodynamics for the control volume, which we are going to explore in the next slide. Now, next is the steady state control volume, for which we are applying the first law of thermodynamics, and the equations which we are getting, that is given as follows. So here we get the Q is the heat transfer rate minus W is the work done by the system is equal to the summation of mass flow rate which is coming out from the system multiplied by, in bracket, enthalpy plus square of velocity divided by 2 plus gravitational acceleration multiplied by height, okay, minus the mass flow rate, summation of mass flow rate which is coming inside the system plus enthalpy, multiplied by, in bracket, enthalpy plus square of velocity divided by 2 plus gravitational acceleration multiplied by height of this mass which is entering into the systems. Now here the steam which enters in the turbine is having a very high enthalpy. And what is enthalpy? It is nothing but summation of internal energy plus flow energy. And it does the work on the blades and it exits at a lower enthalpy. Now, this equation above quantifies what is the work output. Now we will see certain examples of steady state control volumes. So first is the nozzles which are used for the fluid acceleration. Example, rocket nozzles. Next is the diffusers which are used for the fluids to decelerate and rise its pressure. Example in jet engine inlets. Next is the heat exchangers which are used to transfer the heat between the fluids without mixing. For example, the engine radiators or the car radiators. Next are the turbines or the compressors which are used for conversion of energy between work and the fluid enthalpy. Now in case of a nozzle, the steady state assumption simplifies to design. For instance, a rocket nozzle's divergence shape is optimized using mass and energy conservations to maximize the effect of thrust which we are getting at the output. Okay. Now we can see another example in which we are using heat exchangers in a power plant that transfer heat from steam to cooling water. The mass flow rate of the steam and the water remains constant. The temperature stabilizes under the steady state operating conditions. Now these examples show how the steady state analysis underpins the real world engineering application. Now in the next slide, we will see a small example on a nozzle